We've been giving a lot of attention to our old friend glucose, the monosaccharide glucose, that is the building block of things like glycogen and starch and chitin. And what I want to do in this video is give a little attention to another fairly prominent monosaccharide, and that is fructose. That is fructose, often known as fruit sugar. And on its own, as a monosaccharide, it is actually the sweetest of all the sugars, fructose. And so let's compare the two. So the first thing that might jump out at you, and I encourage you to do this, actually these two molecules, these would be helpful ones to actually just be able to draw on your own, because you will see these many times in your biological and in your chemistry and your organic chemistry careers. But if we just compare these two, we see that they both have 6 carbons. So for both of them, the chemical formula, you would have 6 carbons. And then you see that they both have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They both have 12 hydrogens. And to round it all out, they both have 6 oxygens. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So they both have 6 oxygens. So they have the same chemical formula, but they are different molecules. So that makes them isomers. And as we will see, they are structural isomers. The different constituents, the constituent carbons, hydrogens, and oxygens are bonded in a different way, which makes them structural isomers. And when you inspect it a little bit, there's one main thing that jumps out at you. On the glucose molecule, when it's in its straight chain form, we're going to think about them both in their cyclical forms in a second. But when they're in the straight chain form, the glucose molecule has a carbonyl group at the number 1 carbon. If we start numbering up here, so if we start numbering 1, 2, 3, 4, 5, 6. The glucose straight chain has a carbonyl group at its 1 carbon, while the fructose molecule has a carbonyl group, let's see, 1, 2, 3, 4, 5, 6, at the number 2 carbon. Remember, carbonyl group is just a carbon double bonded to an oxygen. So it has a carbonyl group bonded at its number 2 oxygen. And that's the main structural difference. Even if you look at the way that I've drawn these, a hydroxyl group, you have 3 hydroxyl groups on the right side, then you have 1 on the left, 3 on the right, 1 on the left. And so the main difference is just what we did over here. And just to get a little bit more experience with our names for our different functional groups, when we studied glucose, we knew that, look, if you have a carbonyl group that's at the end of a carbon chain, so this carbon in the carbonyl group is bonded to a hydrogen and then the rest of the carbon chain, you would call this right over here, you would call this an aldehyde functional group. Aldehyde functional group, and it makes the entire molecule, allows it to be categorized as an aldehyde. Over here, where the carbon in the carbonyl group isn't at the end of the chain, it's in the middle of the chain, or it's in the midst of the chain, so to speak. It's not exactly in the middle, but this carbon is bonded to 2 different carbons. We call this molecule a ketone, and this would be a ketone functional group because it's bonded to 2 carbons. So this fructose would be considered a ketone. And now let's think about how it might form a cyclical form. And as we've talked about before, the straight chain and the cyclical form, they can be in equilibrium if they are in an aqueous solution. And what I'm drawing here, these aren't the only forms that glucose takes on, but if you were to look it up in a textbook or on the internet, you will most typically, and this is what is most prevalent in nature as well when you're talking about the cyclical forms, find glucose in a 6-member ring right over here, where 5 of them are carbons and then you have an oxygen, while fructose is most typical in a 5-member ring, where 4 of them are carbons and then 1 of them is oxygen. Glucose can form a 6-member ring. When you have a 6-member ring, when you have a carbohydrate that involves a 6-member ring where one of the items is an oxygen like this, you call this a pyranose. So that's a carbohydrate ring where it has 6 members, one of which is oxygen. And when you have 5 members, one of which is oxygen, this is called a furanose. Furanose ring. And actually fructose can be found in either a furanose form or a pyranose form, but the furanose form is the one that's most typical. And when people think of fructose as a ring, they most typically think of it in this form. Well, how does this form form, especially in comparison to what's happening in glucose? Well, what we saw in glucose in both cases, what you're going to do is have an attack on the carbon that's part of the carbonyl group. So over here, that is the number 1 carbon. This is the number 1 carbon here. And over here, this is the number 2 carbon. This is the number 2 carbon. The number 2 carbon right over there. And in both cases, you have, if you want to form these forms, over here we had the oxygen in the oxygen in the hydroxyl group attached to the number 5 carbon. The oxygen in the hydroxyl group attached to the number 5 carbon. This is the 1, 2, 3, 4, 5 carbon. This oxygen is what forms the bond, is what forms this bond up here when you were talking about glucose. And over here on fructose, once again, we look at the number 5, the oxygen on the hydroxyl group on the number 5 carbon. So we look at this hydroxyl group right over here. That's this hydroxyl group right over here. And this oxygen forms a bond with the carbon in the carbonyl group. And when that happens, that allows one of these bonds, in these double bonds, or one of the 2 double bonds, to instead be released from the carbon and then essentially form a bond with a proton floating around. That proton is actually likely to be involved in a hydronium molecule. And the same thing would happen in glucose right over here. This one of the 2 double bonds could now be used to form a bond with a hydrogen proton. And so it's essentially the same mechanism. The reason why this is a 5-member ring involving 4 carbons versus a 6-member ring involving 5 carbons is just the carbonyl group is kind of one further down the chain than it is in the glucose. And so that's why this forms this pentagonal shape right over here. And we've talked about in other videos. Fructose, well, I've already talked about it in this video. Fructose is the sweetest of all of the monosaccharides, the sweetest sugar. And when we talk about table sugar, the sugar that you might put into your tea or your coffee, that table sugar, that's called sucrose. Sucrose, and it's a disaccharide made up of glucose and fructose. And the way that you form the bond, it's still happening through our dehydration synthesis, where you would have the oxygen on the number 1 carbon in glucose. This one over here, let me do this in a color that I have not used yet. See, I've used almost every color, so this is difficult, but I'll just use this green. This oxygen essentially can form a bond with the number 2 carbon on the fructose. And when it forms that bond, then this bond right over here can be, let me do that in a different color. This bond can then go back to the oxygen, or if you really want to think about it in another way, it can then be used to form a bond. It can be used to form a bond with some hydrogen proton floating around. So essentially, it's going to be a carbon bonded to an oxygen, which is then going to be bonded to another carbon, and then someone else can, some other water molecule might be able to sop up this hydrogen proton right over here, and then you would have your bond, the type of bonds that we're familiar with, these glycosidic linkages that we have when we have dehydration synthesis. These linkages that are really the basis for how we start with monosaccharides and we create disaccharides, and if we keep going, we could create polysaccharides. So sucrose is one way to think about it. If I have my glucose up here, actually, let me just draw it this way. So you have glucose, you have your glucose forms a glycosidic bond with your fructose, with your fructose right over here, and that's what sucrose is. And to really visualize it properly, you kind of have to flip this fructose over and then move it up here, and then this character can then form a bond with this carbon right over there.